we're going to be talking about how to sketch graphs of functions based on their derivatives. So we begin with our function, which in this case is f of x equals 1 plus quantity x minus 2 to the 5/3. The first thing we want to determine is when this function crosses the x-axis. We can determine this by solving the function when the function equals 0. Doing this, we determine that the function indeed crosses the x-axis at the point x1, or f of x1. Next, we look to find our critical points. To find our critical points, we set up the first derivative test. We take the first derivative of our initial function. When this new derivative function outputs positive values, we know that the slope of the function is increasing. When this function outputs negative values, we know that the slope of this function is decreasing. We found our derivative simply by taking the derivative of this function, and we only had to apply the chain rule, so it was rather simple. And next, we are able to determine that our function, the function value for our derivative is 5/3 quantity x minus 2 to the 2/3. Setting this equal to 0, we'll find our critical points. Critical points are points that determine characteristics of the function, such as minimum, maximums, but also points in which the slope drastically changes. But by setting this function equal to 0, we are able to determine that we have critical points at -2 and 2, and by testing the intervals for between negative infinity and -2, between -2 and 2, and between 2 and infinity, we are able to determine that our function is always increasing. Next, we determine the concavity of our function. We can do this by setting up the second derivative test. By taking the derivative of our first derivative, we are able to ascertain the points on our function when concavity is upward sloping and downward sloping. This is determined by the points when the intervals during which the second derivative is positive. When the second derivative is positive, concavity is upwards. When the second derivative is negative, concavity is downwards. Having determined all this information, we are able to calculate values, which we will be able to utilize for our graphing of the function. And first thing we find is, in fact, where our 0 point was, which we said was at point 1, which we can see here, is at point 1. Next, we are able to find the critical points that we located earlier, namely at f2, x is, y, f of x equals 1, and at f of -2, f of x equals 10.7. Finally, we are able to notice that the derivative of the function is increasing for all values of f prime of x, which tells us that our slope is always increasing, and our concavity is downwards until 2 and upwards after 2. So you can see downwards concavity shifts to upwards. Next, we look at our next function. Our next function is stated as the square root of x over x minus 2. This, as you can see, is much different from the last function, in that it is a square root, therefore has many limitations. We set it equal to 0, determine that at f sub 0, the function equals 0. And f of x cannot equal does not have a value or a valid value between intervals 0 and 2 for the points. In our first derivative test, we find our critical points. Again, we have to apply a law of math this time because we have to deal with the square root in addition to a fraction under the square root. So we must apply both chain and the quotient rule, we eventually determined that our derivative function is negative 1 over x minus 2 times x to the 1 half times x minus 2. And then we'll notice that the interval between 0 and 2 contains still valid values. And when we solve, when we set the denominator of the equation equal to 0, we're able to find those limits of function at those values. Or rather, whether the slope of the function is increasing or decreasing. Determine then that taking infinity to 0, the slope is decreasing, and for 2 to infinity, the slope is decreasing. Finally, we determine the concavity of the function. We take the second derivative test once again, and as was noted, there is a great deal of math to this. And we eventually determine that our concavity is equal to the points which the function is undivided. We set the numerator and denominator to 0, and we determined that our inflection points for concavity are at 0, 1 half, and 2. Notice again that a point fell into the range if we said no value for f of x can exist. Therefore, we can disregard it, though we will test it for significance later. We notice that in the interval from negative infinity to 0, the slope is decreasing, and from 2 to infinity, the slope is the concavity is upward, and the concavity is downward from the infinity. Finally, we can draw the graphs and calculate the values, which we'll be utilizing. For f of x equals 0, we determined that was our 0, our crossing of the axis. And we could plot that here. We also determined that 2 was one of our critical points. However, the function approaches 2, but the point does not exist because the function approaches infinity. Therefore, we can take it up as if it were an asymptote up here. Finally, we again tested that point right in between here and found that it does not exist. And remembering that our interval only runs from 0 to 2 in the range which no points exist, we are able to graph our function. Looking here, we see it is decreasing, and it has a downward concavity. So we can come up there, and we also notice that our function is decreasing with an upward concavity, and since our function is a square root, we are able to determine that we should have an asymptote at x equals 0. Therefore, we can draw that as seen here, and that completes the sketching of our function.